Hello, it's Keith here, and this is lesson 1 of the advanced series of my Z80 tutorials. Now, the advanced series is going to continue from where the basic series went to. We're going to be learning things that are just general facts about the Z80 and how to use it. So it's not going to be related to one specific computer system or another, and it's not going to be specifically geared towards the game programming that we've been doing in the multi-platform series either. So like today we're going to be looking at binary coded decimal, and all through the advanced series we're really going to be sort of covering things in more detail that we covered in the basic series, or covering things that weren't covered at all like today, where these are abilities or ways of using the Z80 that no matter what you're doing you may need to know. They're not as essential as the stuff in the basic series, but they're things that we do want to learn about, so we're covering them now. They will go into the advanced series. So if you do want to know more programming methods for the Z80, continue watching the advanced series. Now, as I've already said, we're going to be doing binary coded decimal today. This isn't something we've really mentioned before, so let's discuss first what that actually is and why we might want to use it. Now, in the multi-platform series, we've been creating this little text adventure game, and we've come to the point where we want the ability to give the player a currency so that they can collect money and then maybe spend it later. The idea I had is that this sort of currency would be quite large, so you would be able to collect thousands or millions of dollars or whatever the currency was. Now, when you're doing numbers in assembly, of course, numbers up to 256 are very easy because you can use a byte. 65536 you can use a word. Now when you get bigger than that you could start merging the words together, but even if you do that you do have a more serious problem if you're trying to show those values to the screen, because you want to convert them to base 10, and the way what you really need to do for that is you need to divide by tens to work out how many ones, tens, hundreds, or thousands there are. So if you're showing a currency of millions or tens of millions and you're needing to do it quickly, now that might not be true in a text adventure, but if it was if you were trying to create Space Invaders, you wouldn't want your processing power used by showing your score. You'd want to keep all of that processing power for the more important jobs of showing the enemies on screen and the graphics and things. And so what you can do is you can use this thing called binary coded decimal. Now binary coded decimal is very simple, so I'll just explain it to you now via the powers of Notepad. So let's move my Notepad in here. So suppose you had a number 1, 2, 3, 4, 5. Okay, let's just get a calculator up here. So 1, 2, 3, 4, 5 in decimal, that is. Now in hexadecimal, that's 3039. Okay, so if you think of a 2-byte number, I'll just expand this to 4 bytes here. So if you're using 4 bytes to represent it, in hexadecimal that would be 3039. Well, okay, that fits fine in our 4 bytes, but the problem is, as I say, we're going to struggle to actually get that into text for the screen. So what we really want is we want a simpler way of storing it that we can pull it out more quickly, that the computer can still reasonably work with, because of course the computer needs to work in binary and hexadecimal. And what we have is this rather strange thing called binary coded decimal, and what it does is it uses the bytes, but it uses them in a kind of simplistic way that allows the functionality to still work, but it gives us the ability to quickly convert back to decimal, and it's really incredibly simple what it does. Now all you do is you split the digits up and you store them in different bytes. So in normal binary coded decimal, what you would store is you would store here 01, 02, 03, 04, 05. So you're using 1 byte per digit, and this is actually what ChibiAkumas does, and the score in ChibiAkumas is a binary coded decimal, and it's in this format where each byte only stores 1 digit. Now of course that's very, very wasteful, because each of those bytes can store up to 255 and we're only using them to store up to 9, so that's not really very efficient. It's also not really the way that the Z80 is designed to work with binary coded decimal. As I say, this is the way that ChibiAkumas uses binary coded decimal for the score, but to be honest, when I wrote my game I didn't really understand binary coded decimal above the very basic level. I only actually learned it over the last week or so when I started working out the contents of this tutorial. So anyway, this is the sort of most basic form of binary coded decimal, but the one that we're going to look at today, and the one that the Z80 is really designed for, is what's known as packed binary coded decimal. And what that is rather than using a byte to store each digit, we use a nibble, so half a byte. And so 4 and 5 are stored in the same byte here. 2 and 3 are stored in this byte here. And then this byte would store 0 and 1. And these two here would be unused. Now, apart from the advantage of saving memory, if you were doing a 100-digit number, you would now be using 50 bytes rather than 100. Apart from just that benefit, the Z80 does have this rather special DAA command. I think it's decimal adjust accumulator it stands for. And if we use this packed format, that command will actually do all of the heavy lifting for us. It will do all of the work for us. And it really allows us to almost carry on it as if nothing's changed, as if we're just working with normal hexadecimal numbers, but we get the benefit of binary coded decimal, and we get the benefit of that packed binary coded decimal almost as a sort of free extra. So, well, what's the problem with binary coded decimal compared to hexadecimal? Well, the problem's simple. When you're doing addition and subtraction, if you think of a number like 99 in binary coded decimal, if you want to add 11 to that, that should really go to 0. And then you would want to add the 1, the carry, to the next byte along. So if you do 99 plus 11, you would want that to go to 0, 0. And you would want a carry of 1. Now, okay, but if you use the add command's a hexadecimal command, obviously. So that 99 is going to change to AA. And the carry isn't going to be set. Well, that's not great, but it doesn't matter, because DAA will figure all the problems out for us. And once we run our DAA command, you will get, well, no point in typing it, you get exactly this. So whatever the previous command was, whether it was add or subtract, DAA will correct the hexadecimal down to valid binary coded decimal, and it will change the carry flag to represent any additional subtraction that needs to be made from the next digit along. And it does everything for us. So let's just prove that. We're going to be working entirely in WinApe today. As I said, all these commands are common to all Z80 systems. These are Z80 commands, they're not Amstrad commands, they're not Spectrum commands. And as I've said before, I personally believe that WinApe is the best assembler system for beginners. So that's what I always work with when I'm trying to do these fundamental things. So let's assemble this program and let's have a look at this first little bit here. So we're going to do basically what I just showed. We're going to load in 88 into the accumulator. We're then going to add 22, which will push it over the limit for binary coded decimal. Then we're going to run the DAA command, and then we're going to load A with 11, and then we're going to subtract 22, which will push it under the limit of binary coded decimal. It will go below 0 to FF. And then EF, I think that is, sorry. And then we're going to do the DAA command again. So let's just compile that. It's compiled. And let's do call and 8000, and the debugger will pop up. Okay. So we're about to run the first command, which is just very boring. So 88 has been loaded into the accumulator. Now we're subtracting 2, so it has become AA. Okay, well that's not valid for binary coded decimal, and the carry flag is currently 0. So when we run the DAA command, the accumulator has changed to 10, and the carry flag has been set to 1. And that's because the carry knows that another digit needs to be added to the next one. Okay, so let's continue with our subtract command. So if I press F7 again, we've now loaded A with 11. Now we've subtracted 22, and A has become EF. Again, that's not valid for a binary coded decimal digit, and the carry is currently 1. That's because it has rolled over. It knows it's rolled over, and because of the subtraction going below 0. But then when we run the DAA command, the carry flag is still 1, so it still says, hey, you need to subtract something. But now the digits have changed. The accumulator has changed to 89, which is the correct valid binary coded decimal value. Okay, well, that's all quite theoretical. As I say, the take home of this is the DAA command will convert the accumulator and make it work as if it was always binary coded decimal, even though the previous commands were working as if things were hexadecimal. Now, how do we use this in practical terms? Well, I've created this little test program here, which is going to demonstrate subtraction, addition, and comparing of two binary coded decimal strings. So let's have a look at the way we're storing our strings here. Now, here's the strings. Now, there is an important sort of thing to know about these. They are actually working in reverse order. So the least significant bit is here, and the most significant bit is here. So if I was going to show this in decimal, it would actually be 0119000000. And as I said, it's a decimal number. It's not a hexadecimal number because it's binary coded decimal. The and symbol, of course, is just because we're working in nibbles, so it makes everything neat. But as I say, these are binary coded decimal numbers. So that is the value of this below. And so what we're going to do is we're going to use this as our sort of base value. We're then going to use these values for addition and subtraction. And then we're going to use these values for comparing to see how that result compares. Okay. Now, many of our binary coded decimal commands are going to start from the least significant byte first as they're processing. The addition and subtraction, for example, you're always going to add the lowest value and then carry on. But some of our commands are going to need to start the other way around. For example, showing to the screen, quite an important command there, but we're going to show the first digit is going to be on the left, and that is going to be the most significant byte in the string. So as I just wrote here, the first byte we want to show is the one all the way over here. And we're going to make a quite nice, simple little command to do that. When we're working with binary coded decimal, we're going to always use two parameters for our addition subtraction commands. Now, the first one is going to be DE, which is the destination. That's where we're going to write to. And then HL is going to be the parameter, so the amount that we're adding to the destination, the amount we're subtracting to the destination, or what we're comparing to the destination with the compare commands. So we're going to always use DE, we're going to use HL where there's a second parameter, and we're going to use B as the number of digits in the binary coded decimal variable. So this is going to be constant to all of these examples. Now, some of them may only need one parameter, but as I say, that's the general template. And so where we need to be able to show, where we need to start from the right and work left, we're going to write a little command to do that for us quickly called bcd_getEnd. And all that does is it backs up BC because we don't want to change anything we don't need to. It then sets BC to be the value in B minus 1. Because we don't want to go past the limit of the variable, we want to go to the last digit and then point to that last digit. So we're subtracting 1 there. We just add that to DE and then to HL, and then we return. We're adding to both because in most cases we are using two parameters. Now that's not always the case, but I figured it was better to use one function for all our things rather than write two, one that only affected HL and one that affected HL and DE. So what are we going to do in our second example then? Okay, well, let's have a look. Well, first we're going to show this string. We've got this show test function, and all it does is because we're going to use this many times, I've created a quick function. All it does is it loads the value we're going to show into DE, loads B with the length of the value, all the values of 5 in this example, and then it runs the bcd show command. The bcd show command, let's have a look at that now. Well, first we go to the end because we want to show the most significant byte first. Reads in a byte, takes the high part, shifts it across, adds it to 0, the character 0 that is, and then prints it. We want to do that again for the low part, so we load it back in. We then decrease our counter because we want to move to the next byte along to the left of the digits, the less significant byte. We then do our AND here to get the least significant nibble of the byte that we just read in, add 0 again, and print it to screen again. And then we just loop. Now this is much simpler than doing it with hex, and it's many times simpler than if we were converting a hex value to decimal for the screen, or for characters for the screen rather. So being able to do each byte in such a simple way means that we can get that data to the screen much faster, and that would be very important if we were using a 20-digit score for some crazy pinball game or something. We need that processing power for other things, so we sacrifice the memory of this less efficient binary coded decimal storage, and we get the speed when we're showing it to the screen. So that's our show command here. Okay, So then we're going to do a subtract command. So this takes two parameters. The destination is the one that is our main parameter, and HL value 2 is what we're subtracting. So we're going to run this subtract command, which we'll have a look at in a moment. We're then going to run this second subtract command. Each time we're showing the value to the screen, just so we can see how it changes. Then we're going to add the one here, and then we're going to add the one here. Now if everything's worked fine, our value should end up exactly the same place as it started here. And then we've kind of proved our subtract and addition work there. So the last thing we're going to do is we're going to do some compares. And we need to put some breakpoints here because we want to see the result. The compares change the carry flags, and they do it in the exact same way as the CP command would do it. So I've tried to recreate the CP command's functionality using this BCD function. So if we just put these breakpoints here, then we'll be able to see the state of the carry flag, which of course should be 1 if the value is lower. The NC should be 1 if it's higher, or the same. The Z flag, which is if it's 0, or if it matches what was compared to, and then Z if it doesn't match, if it's not 0. Okay, so there we go. So let's have a look at our subtract command that we're going to use then. So the first thing we need to do, we're going to be using the SBC and ADC commands, because as I said, we need to start on the least significant byte, but if there's a carry, we need to add that carry to the later bytes as we process those. So there is no clear carry flag command in Z80. Of course, the CCF is complement carry flag. So the quickest way to clear the carry flag is to do an OR A, because that will make no difference to A, but it will clear the carry flag. So that's what we do here. Then we load in our byte from DE, the destination. We use the HL SBC command, which means we don't need to load that into another register. So that will have affected A by subtracting the value in the address HL with the carry added. And then we use our DAA command, which fixes the binary coded decimal, as we've already discussed. And then we store it back in. We then just move along to the next byte, and we repeat until B is 0. Well, that's pretty simple, isn't it? And let's have a look at add. Well, it's practically the same command. All we do, we clear the carry flag, load in from DE, we add with carry to the value in the address HL. We then use DAA again, and we store it back, and that's it. And this is the beauty of DAA. It turns what would, if we were trying to program this ourselves, this would be a nightmare command to do. But it's just one command, and it's a fast command as well. So it makes binary coded decimal speed-wise pretty much as efficient as anything else. So it's really good command. And of course, it's not really designed for games. This was put in for database functionality and things like that. This was this was the people programming spreadsheets who were thinking about this, not the pinball programmers wanting their long digit scores. But as I say, it's very fast command, very powerful. So okay, so we've got our add and our subtract there, very simple command. Okay, so let's have a look at the compare command then. So again, we start from the end of the binary coded decimal variable, because we want to look at the most significant byte first, because if the most significant byte is greater, then we know the whole thing is greater. If it's lower, we know it's all lower. So we start from the end, we read in the first byte from DE into A, we compare to the one in HL. If it's smaller, then we return, because we know that it's small. We know that the comparing one is smaller. If it's not 0, then we know that they aren't the same, and that must mean they're higher, so we return again at that point. Now if we've got to this point, then actually that byte matched with the one we were comparing to, and so what we need to do now is we need to proceed to the next less significant byte and compare that. So all we do is we decrease our two counters, our 2 pointers, and then we jump back up here until we get to the end of the binary coded decimal variable. Now if we get to here, then all of the bytes we compared were the same. So all we do here is we do an OR A to clear the carry flag, and then we return. And this will allow us all of the basic functionality that the Z80 gave us, but this time using binary coded decimal. Okay, so let's have a look at this then. So if I do call and 8100, this will start the test program, and let's see what happens. Okay. Now I'm just going to move this out of the way a moment, because we're going to have a look at the code and the screen values first. So you can see here 011900. So you can see here first we're going to subtract value 2 here from value 1. And you can see here that this has happened and that has worked okay. Now the next thing we're going to do is we're going to subtract just 1 from that value just to check that the carry is working. And you can see it's all gone down by 1, so it looks like that's working again. And that was here. So now we're going to add that value 3 again, basically adding 1, and which go back to this value, which of course it does. And then we're going to add the first value again, meaning that we've ended up with the exact same value we started with. Okay, not very useful for the point of, well, why would you be adding what you just subtracted, but it's a great example. And you can see here that we can show them all on screen. Now the other thing we've got the function of is the compares. Now I don't actually use the compares in any case here. I could have shown labels to the screen saying, oh, this is higher, this is lower, but it didn't really make any difference. As I said, this example was really trying to teach the functionality of the DAA command and how to use binary coded decimal. It wasn't trying to make it into a practical example, because we can do that later in the multi-platform series when we're game programming. So let's have a look. So we've just done a compare, and we've done a compare of value 1 with itself. And so, well, the carry flag isn't set. Well, that's what we'd expect, because it's not higher. And then the 0 flag is set because it's the same as the value we compared to. And so this is the next compare we're going to do. So this time we're comparing it with the one that is higher. And you can see this time the carry flag is set because it's smaller. Because A is smaller. So that's the functionality we'd expect from that. And in the last one we're comparing to the value that's lower, and so because A is higher, the carry flag is cleared and the 0 flag is not set. So there we go. So we can use this BCD compare command to do similar comparisons with our normal hexadecimal bytes, but this time we can do them with the binary coded decimal strings. And we would need to do this if we wanted to check if our player had enough money to buy a certain item. We'd need to check how much currency they got, or if you wanted to check if someone had a high score or something like that, you would want this kind of functionality again to be able to compare two strings and just make a judgment on which one was the superior. Okay, so there we go. That's binary coded decimal. I think this isn't something you may ever need. You may be able to write your game without ever using this, and if that's the case, by all means don't use it. But if you're trying to do things that are more mathematical with very large numbers, then this is definitely something you want to be able to do. There is even more advanced stuff with regards to using decimal places. That's not something I'm planning to cover at this point, because again, I don't really think that's something you're ever going to need in game programming. That's certainly something you'd need if you're writing a spreadsheet, but it would seem a bit excessive to use a Z80 system for writing a spreadsheet in most terms. So as I say, that's not something I'm planning to go into in this stage, but if it does come up, then we'll add it later. Anyway, I hope you've enjoyed today's lesson. Okay, and just as a sort of teaser and to let you know what other things I'm working on, I am actually planning on adding Sega Game Gear and Sega Master System, which are basically almost the exact same system, to my tutorials, and also the Game Boy and the Game Boy Color I'm planning on adding. Now the Game Boy and the Game Boy Color aren't actually Z80 systems. They're a hybrid processor, which is almost a Z80 but not quite, but then it's got some other commands added to it. So that's going to be quite a challenge to add that, but I've already got my Hello World example running, as you can see on screen. So I'm hoping in the future you'll be able to build even more systems with my tutorials, and to learn how to do Game Gear and Game Boy as well. Now that aside, the game you can see here is my ChibiAkumas game, if you're not familiar with it. This is now actually available for pre-order from Polyplay, so if you like boxed copies, then you can get this for ZX Spectrum, MSX or Amstrad CPC. So if that's your thing, please go over there and consider pre-ordering that. Well, once again, thanks for watching. I hope you've enjoyed my tutorials, and I hope you'll keep following them, because I'm hoping to be able to teach you enough to write a game like this yourself, because I was a total beginner when I started developing this game, and the original release came out 6 months after I started, and this is the newer release, but the original was almost as good as this. So I think it's really possible that even if you've not done assembly programming before, you can create a game that's reasonably professional standard and that is certainly enjoyable, and aside from the playing reward of it, you will get a lot of personal satisfaction of being able to create your own game and being able to bring something that you wanted to see made into life through your own work. So yep, please keep following. If you want to buy my game, please go ahead and pre-order that. And I hope you'll follow me as I start up with the Game Gear and Game Boy tutorials. Thanks for watching, and goodbye.